Welcome to the Deep Dive. If you're here, you're looking for the essential truth hiding inside the cutting edge of research. And today, well, that truth fundamentally reshapes our view of the cosmos.
It really does.
We are tackling an immense, almost existential question. How many stars are truly single, isolated entities?
Right.
And if they aren't, how does this whole web of companionship, from binary stars all the way down to the smallest planet, how does that redefine stellar life?
It's a fascinating deep dive, and it actually takes us back in time quite a bit. We have to examine the incredibly challenging history of exoplanet hunting.
Okay.
Our sources today, they reveal that long before we had these dedicated space missions confirming thousands of exoplanets, astronomers were already pretty much convinced.
Convinced based on what, though?
Based on statistical mechanics and, well, all these little observational anomalies, they pointed towards companionship being the rule, not the exception.
And the numbers are just staggering when you look at them. We're talking about stellar multiplicity systems with 2, 3, 4, maybe even more stars.
Uh-huh.
And this being far more prevalent than I think most people realize. The sources are estimating somewhere between, 30% and 50% of all stars are part of these multiple star systems.
And that's a key point. They're just the obvious stellar companions, the ones you can actually see or easily detect.
Right, the big ones.
That's the crucial distinction, yeah. Because when we start considering the less obvious, the lower mass companions, the ones that really blur the line between a tiny star and a giant planet,
Okay.
that's when the statistical conclusion becomes really radical. So our mission today is basically to give you the shortcut.
A shortcut to understanding all that astronomical detective work.
Exactly. The work that kind of proved this and why having some kind of companion, whether it's another star or a planet, might actually be a fundamental property of, practically every star out there.
Okay, let's unpack this then. We really have to start with this foundational idea. Single stars, like our own sun maybe, they might actually be the exception, not the rule.
It flips the perspective, doesn't it?
Totally. And to prove that, astronomers basically had to invent this whole spectrum of detection techniques. Techniques tailored specifically to how far apart the companions were.
Yeah, historically, people have known about multiple stars for centuries, right? But initially, you could only really observe systems where the components were, let's say, relatively far apart.
So these are the first category.
We categorize these first ones as visual binaries.
Okay, visual binaries. These sound like the easiest ones to get your head around. They're wide systems.
Exactly. Wide systems where if you look through a decent telescope, you can literally resolve them. You see two separate points of light.
And we're talking really far apart here.
We could be talking hundreds, sometimes even thousands of astronomical units separating them, which means their orbital periods can stretch into centuries or even millennia. It takes patience.
Wow, millennia.
Yeah, and because you can actually see them separately, systematic visual observations over time let you map out their orbital motion.
So you're literally plotting dots on a chart year after year.
Pretty much. You plot the relative positions of the components. Our source material actually points to the sequential positions of a component in the Epsilon Ursae Majoris double system. That's a classic historical example of just how painstaking this process was.
But the payoff is huge, right?
Yeah.
Observing these systems must be fundamental to astrophysics.
Oh, absolutely. Because by tracking that orbit, however slow it seems, and just applying basic celestial mechanics, Newton's laws, Kepler's laws, astronomers can immediately get an estimate of the individual masses of those stars.
You're weighing stars.
You're essentially weighing the stars using gravity as the scale just by watching their cosmic dance.
That's incredible.
Yes, these visual binaries are absolutely critical. They give us the most direct way to measure stellar mass. If you know the period and you know the semi-major axis of the orbit, you can calculate the total mass of the system.
Sure.
Then, by watching how the center of mass, the barycenter, is positioned relative to each star, you can actually break down that total mass into the mass of star A and the mass of star B.
And that feeds into everything else we know about stars.
It forms the absolute bedrock of our understanding of things like the Hertzsprung-Russell diagram. It all comes back to mass.
But okay, the visual method, it obviously has limits. Resolution, mainly.
Exactly. Once stars get too close together, maybe separated by just a few AU or even fractions of an AU,
They just blur into one.
they become indistinguishable, yeah, even through the biggest ground-based telescopes at the time. And this is where the detective work gets really fascinating. This is where spectroscopic binaries come in.
Spectroscopic, so using light spectra.
This was a brilliant leap, really. When the stars are so close they just look like a single smudge of light, their duality, the fact that there are two, is proven entirely by analyzing the light itself, the specific wavelengths.
How does that work?
We rely completely on the Doppler effect acting on the system's radial velocity.
Okay, the Doppler effect.
Yeah,
Like the sound of an ambulance siren changing pitch.
precisely. As these two stars orbit their common center of mass, one star is pretty much always moving slightly toward us, while the other is moving slightly away.
And it shifts the light.
When a star approaches, its light gets subtly compressed towards the blue end of the spectrum, that's a blue shift. When it recedes, the light gets stretched out towards the red end, a red shift.
And this isn't just a one-off thing.
No, that's the beauty of it. The shift is periodic and systematic. If we observe the star's spectrum regularly, over time we see the spectral lines. Well, sometimes they split apart and then merge back together, or they just shift back and forth.
Following a pattern.
Following a predictable cycle, yeah. And that cycle is dictated by the system's orbital period. This periodic shifting of the spectral lines is the irrefutable evidence. It tells us we're definitely looking at two objects locked in orbit.
And you can get numbers out of this, like quantitative data.
Yes, the analysis allows for some really deep quantitative insights. Now, just observing the spectrum shift alone doesn't give you the absolute true mass, unfortunately. It gives you something called the mass function, which often involves this term, m sin I.
Sin I. What's the I?
That sin I is the necessary catch. It represents the inclination of the orbit. Because we're only measuring the velocity along our line of sight, the radial velocity, we don't know the exact tilt of the orbit relative to us.
Ah, okay, so if we're looking straight down on the orbit.
Right. If the orbit is face-on, so I equals 0, we measure no radial velocity change at all. The stars are moving side to side from our perspective.
And if it's edge on.
If it's edge on, I is 90 degrees and sin I is 1, then we measure the full orbital velocity. So the data really only gives us the minimum possible masses for the stars.
So you need more.
Ideally, yeah.
Ah.
Only when the spectroscopic data is combined with other methods can we, fully resolve the system's masses.
And that combination happens in, well, I guess the rarest cases. The ones that have to be lined up just right.
Exactly, the eclipsing variables.
Eclipsing, like a solar eclipse.
Sort of, yeah. In these systems, the orbital plane is almost perfectly aligned. We're talking within a fraction of a degree, with our line of sight from Earth.
That sounds incredibly unlikely.
It is. It's a cosmic alignment lottery. But when it happens, it means one star periodically passes directly in front of the other, from our viewpoint,
And that blocks the light.
causing a temporary but measurable drop in the combined brightness of the system.
And since you still can't see the two stars separately,
Right, the components aren't resolved visually, so the only observable thing we have are those periodic dips in the star's brightness, and this is where the light curve becomes the ultimate tool.
a light curve, just plotting brightness over time.
Creating a really precise graph of brightness over time, plotting every rise and fall, allows astronomers to figure out phenomenal levels of detail. The classic example mentioned in our source material is the Algol system.
Algol.
Okay.
What can you get from its light curve?
Well, the shape and the timing of the curve obviously tell us the orbital period. That's straightforward. But the depth of the main dip and any secondary dip if the other star passes in front,
Uh-huh.
and also the speed at which the light drops and recovers during the eclipse, that reveals the star's actual physical diameters.
Wait, you can get the size of the stars
Yeah.
just from the light dimming.
It's amazing, isn't it? We can figure out the precise size of two stars millions of miles away without ever actually seeing their disks.
That's incredible.
But the light curve gives us even more, really granular details, things like limb darkening.
Rim darkening, what's that?
Limb darkening is this phenomenon where a star's disk actually appears dimmer at the edge, the limb, than it does at the center.
Why does that happen?
It's because when we look at the edge, we're essentially looking through more of the star's cooler upper atmospheric layers, whereas when we look straight at the center, our line of sight penetrates deeper into the hotter, brighter layers underneath.
Okay, I think I follow. And how does an eclipse show that?
Well, in an eclipsing binary, think about when the eclipse starts and ends. As one star just begins to cover the other or just finishes uncovering it.
You're seeing light just from the limb.
Exactly. The way the light dims or brightens right at those moments tells us the extent of that limb darkening effect, which in turn provides physicists with critical data about the star's atmospheric structure, its temperature gradients. It's an incredible level of inference, all derived from just carefully measuring how the light flickers.
Wow. Okay, so eclipsing binaries are like a gold mine if you can find them.
Definitely. And this brings us to the most extreme cases, the extremely close and interacting pairs.
Closer than spectroscopic binaries even.
Yeah, the components of some spectroscopic and eclipsing binaries can be so physically close that their surfaces are practically, well, almost touching.
What happens then?
When they get that close, the gravitational forces, the tidal forces, become incredibly powerful. Powerful enough to physically distort the stars themselves, often into sort of teardrop shapes.
Yeah.
And this is where things get really dynamic. Matter actually begins to flow out of the stars, usually from the larger, more evolved one into the smaller one. It fundamentally alters their lives.
Like a river of star stuff flowing between them?
Kind of, yeah. The sources cite the Beta Lyrae system as a famous example. It's a close pair that seems to be immersed in this shared, very thin, rarefied gas envelope.
And we know this just from the light.
What's truly mind-boggling is that the entire complex physical picture of that system, the gas flow, the shared envelope, it's all reconstructed solely from analyzing the changes in the star's brightness and its spectrum over time. No direct image needed.
It just shows how powerful gravity is, acting as a sculptor on that scale.
Absolutely. And when stars are locked in such tight proximity, Kepler's laws demand extreme orbital speed. The periods become astonishingly short.
How short are we talking?
Really short. The source points out an eclipsing variable called AM Canum Venaticorum. Its orbital period is the shortest known. It's close to 18 minutes.
18 minutes for a full orbit.
18 minutes. Think about that. A full stellar orbit completed faster than, watching a sitcom episode.
That's just hard to comprehend.
It really is. That kind of system is fundamentally different from those slow, stately visual binaries taking centuries. It shows that multiplicity exists across the entire possible scale of gravitational interaction, from incredibly wide pairs to stars practically skimming each other.
Okay, so we've mapped out this whole spectrum of stellar companionship. Now we need to shift gears a bit and get into this realm of extreme mass asymmetry. This sounds like where the definition of star starts to get fuzzy.
Exactly. This is where we start bridging the gap towards planets.
So while most binaries we can easily see have stars of, roughly similar masses.
Right. Maybe one is twice as massive as the other, something like that.
There are pairs that show these tremendous differences.
Oh, yeah. We find systems where one component might be 10 times less massive than the primary star. And the light output, the luminosity, can differ by thousands of times. One is bright, the other is incredibly faint.
And sometimes the companion isn't even a normal star anymore. You mentioned white dwarfs.
That's right. We find components that have already gone through their evolution and collapsed into these extremely dense, small objects, like white dwarfs. The companion to Sirius, Sirius B, is the classic example everyone learns about.
Tiny, like Earth-sized, but super dense.
Incredibly dense, but it's still fundamentally a stellar remnant, It was a star.
Okay. But the real mystery, the core of the problem for planet hunting, lies in what early astronomers called invisible satellites.
Yes. These are objects with such low mass that their own luminosity is basically negligible. They're truly invisible to traditional telescopes simply because they don't emit enough light to be seen directly against the glare of the primary star.
You find it by its gravity. That's the only way. Their presence is established purely by studying the tiny, minute, periodic oscillations in the movement of the bright primary star.
The wobble again. The wobble again, yeah. If the primary star we can see is wobbling slightly back and forth or in a little circle, something unseen must be gravitationally pulling on it.
And measuring that wobble must be incredibly hard.
It requires extraordinary observational patience and immense accuracy. The sources point to the 61 Cygni system that was thoroughly studied by the Russian astronomer A.N. Deutsch. This kind of historical astrometric work was all about trying to detect these very faint gravitational tugs.
And what kind of masses were they finding for these invisible satellites? Were they star-sized?
Well, this is where it gets interesting. The known invisible satellites they could detect back then had masses around, say, 0.01 solar mass, 1/100th the mass of the sun.
Okay, how does that compare to planets?
Well, 0.01 solar mass is roughly 10 times the mass of Jupiter.
10 Jupiters. That sounds huge for a planet, but small for a star.
Exactly. To an astronomer, that's tiny for a star. Yet, these objects are still technically considered stars, or maybe more accurately, very dim brown dwarfs.
Why still call them stars?
Because they are thought to be self-luminous gas spheres, they've generated some internal heat from gravitational contraction, even if they aren't achieving sustained hydrogen fusion like a proper star. They're not just cold planets shining only by reflected light.
Ah, okay. There's a bit of internal glow.
A little bit, yeah. But the source material really challenges that dividing line based on self-luminosity. It argues that the difference between a gas giant planet, like Jupiter, and these faint, invisible stellar satellites, it's not fundamental.
Not fundamental. How so?
Well, chemically, they're pretty similar, right? Both consist mainly of hydrogen and helium. The only real difference is the total mass.
And mass dictates everything else.
Mass dictates the internal pressure and temperature. More mass, more pressure, higher core temperature.
And this leads to that critical thought experiment you mentioned, the planet-star continuum.
Precisely. The idea is if you took Jupiter and somehow made it, say, 10 times more massive than it is now,
Its core would get hotter.
its core temperature would rise enough, just from the increased pressure, for it to become weakly self-luminous. It would actually cross that somewhat artificial line we draw. It would become a faint red dwarf, maybe with a surface temperature of 1,000 or 2,000 Kelvin. Still cool for a star, but glowing on its own.
So it's not a sharp cutoff, it's more like a gradient.
Exactly. We're talking about a whole population of low-mass objects that exist on this continuum. It's a gradient of gravitational pressure and temperature, not some sudden switch from planet to star.
Okay, that makes sense. The most massive self-luminous things are giant stars. The least massive are large planets.
And in between, you have this whole range of barely self-luminous brown dwarfs and these invisible satellites.
And the data suggests this whole population, including these dim companions, is actually really common.
Yeah, the prevalence seems significant. Even just looking at the ones they could detect back then, the ones around 10 times Jupiter's mass, the sources state that within just 10 parsecs of the sun, that's about 33 light years, a volume containing roughly 53 known stars, 5 of those stars had confirmed invisible satellites.
5 out of 53, that's nearly 10%.
Almost 10% of nearby systems hosting these quite massive unseen companions.
Wow. Okay.
And this immediately leads us straight to the central problem of finding planetary systems. Because if companions that are 10 times the mass of Jupiter are reasonably common,
Then logic suggests.
that there must be even smaller, maybe ultra-invisible satellites out there. Companions that are practically indistinguishable mass-wise from large planets like our own Jupiter or Saturn.
So the search for the smallest stars automatically becomes the search for exoplanets?
Pretty much, yeah. The underlying gravitational physics is exactly the same. The scale of the effect is just smaller and harder to detect.
So this brings us to the moment when astronomers really started to formally think about designing experiments specifically to detect planets around other stars.
Right, they had to get pragmatic.
And they had to define like the easiest possible target they could imagine, right?
Yeah.
What was that target?
Their benchmark was a solar-type star, so something like our sun, located relatively nearby at 10 parsecs, about 33 light-years away. And orbiting it, the easiest planet to find would be a massive Jupiter twin.
Makes sense. If you can't find a Jupiter right next door, finding an Earth is going to be impossible.
Exactly. Finding Earth or Mars analogs was considered pure fantasy at that point. So this section really details the 3 main theoretical methods they considered, and crucially, why back in those early days, every single one of them was deemed basically impossible.
Okay, let's break them down. But with method 1, astrometric wobble, proper motion. We mentioned this worked for the heavier, invisible satellites.
Yeah, they tried to apply the same technique, but for a true planet. Astrometric wobble, remember, relies on meticulously tracking a star's slow, straight movement across the sky, its proper motion.
And the planet makes it wobble.
A massive planet orbiting the star forces the star itself to orbit their shared center of mass. This results in a tiny, periodic, S-shaped or circular, wavy oscillation being superimposed onto that straight, proper motion path we observe.
And the timing of the waves tells you the planet's orbit.
Right. The wobble is dictated by the orbital period of the planet. So for a Jupiter twin system orbiting like our Jupiter, that period would be about 11.9 years.
Which means you need observations spanning decades to even see one full cycle.
Decades, yes. Patience was key. But the real killer was the precision barrier. Calculations, famously done by the astronomer O.L. Struve, showed just how small this wobble would be.
How small are we talking?
For a Jupiter twin at 10 parsecs, the maximum deviation the size of that wobble would be a minuscule 0.00005 arcseconds per year.
0.0005 arc seconds. Wait, an arcsecond is already tiny.
Yeah.
Like the width of a hair from 100 feet away.
Exactly. And this is 5/10,000ths of that.
Why was that considered so impossible to measure?
Well, think about looking through Earth's atmosphere. Just the normal atmospheric turbulence, the shimmering you see, it smears the image of a star into a blurry blob that's typically 0.5 to maybe 2 arcseconds wide.
Okay.
Now try to detect a wobble of 0.000005 arcseconds within a blur that's maybe 4,000 times wider. It's completely lost in the noise. Struve correctly called this value negligibly small and utterly beyond the precision of astronomy at the time.
So the method worked for companions maybe 10 or 20 times Jupiter's mass.
Right. The heavier, invisible satellites produced a just detectable wobble. But for true planets, no chance from the ground.
And that's a really critical distinction. The technique was great for finding faint stars or brown dwarfs, but it just lacked the necessary finesse for planet.
Absolutely. And those historical attempts you sometimes hear about trying to find planets using ground-based astrometry back then, they were often disputed later on.
Why?
Because the systematic errors in the measuring instruments themselves over decades of use tiny drifts, imperfections were often larger than the actual planetary signal they thought they were seeing. It was basically a technological dead end until space-based observatories came along much later and revolutionized astrometry.
Okay, so astrometry was out for planets. What about method 2? Spectroscopic radial velocity. The Doppler shift method.
Right. This is the method that ultimately proved to be the most successful decades later.
Yeah.
But early on, it also seemed impossible for finding planets.
We know it works for close binary stars.
Yeah.
Why was it so much harder for a planet?
It's all about the massive asymmetry again. A planet is so much lighter than its star.
So the star barely moves.
Exactly. The shared center of mass is usually deep inside the star itself. So while the star does wobble due to the planet's gravity, the resulting change in the star's velocity along our line of sight, the radial velocity, is incredibly tiny.
How tiny did Struve calculate this one would be?
His calculation, again, defined the barrier. The periodic change in the star's radial velocity caused by a Jupiter twin wouldn't exceed about 10 meters per second. 10 meters.
10 meters per second. That sounds fast. Like sprinting speed.
It sounds fast to us, but for a star, it's nothing. Remember, the star's total radial velocity, just its overall motion towards or away from us through the galaxy, could be tens of kilometers per second. So this 10 meters change is only about 1,000th of the star's overall velocity.
Okay, tiny in astronomical terms. And how does that translate into the light shift?
That's where it really hit the wall. That tiny velocity shift corresponds to an almost undetectable shift in the wavelength of the star's spectral lines, just 0.00001 angstroms. That sounds even smaller than the astrometric wobble number. It is, in its own way. And this is where the fundamental physics of starlight itself defeats the detection method, at least back then.
How so?
Spectral lines aren't perfectly sharp, mathematically thin lines. They have a natural, inherent width. This is due to things like the thermal motion of atoms in the star's atmosphere, the star's rotation, and this width is usually tenths of an angstrom, sometimes even more.
Ah, so the line itself is already wide and fuzzy.
Exactly. Now you're trying to measure a shift of 0.00001, a shift maybe 100 or even 1,000 times smaller than the natural width of the line itself. It was just technologically impossible to pick that tiny shift out from the inherent fuzziness of the line.
Wow, okay, so 2 methods down. Astrometry and radial velocity, both needing incredible precision, both defeated by the limits of the instruments and, well, the universe itself.
The sheer magnitude of the challenge they faced back then is really stunning when you think about it. They knew the signal had to be there based on gravity, but they just couldn't possibly pull it out of the noise.
So what was the third option? Method 3. Photometric transit, measuring brightness dips.
Right. This relies on systematically, patiently measuring a star's brightness, hoping you'll catch the incredibly rare event where a planet happens to pass directly across the face of the star's disk from our point of view, like Venus or Mercury transiting our sun.
Now, this one actually seemed a bit more promising in one way, right? The signal strength.
Yes, that was the key difference. A Jupiter-sized planet transiting a sun-like star would dim the star's light by about 0.01 stellar magnitudes. Now, that's still small, but it was a change that the early electrophotometry electronic light measurement could, theoretically, register.
So unlike the other 2 methods, the signal strength wasn't the main problem.
Correct. The sensitivity was potentially there, but the geometric constraint made it, as the source says, practically unrealistic as a way to actually find planets systematically.
You need that perfect alignment again.
You need an absolutely perfect alignment. The transit method only works if we, the observers here on Earth, happen to be almost exactly in the plane of that planet's orbit around its star.
And almost exactly means.
We're talking incredibly precise alignment. If our viewing angle deviates by just 2 or 3 arc minutes from the orbital plane,
The planet misses the star's disk.
it'll pass just slightly above or slightly below the disk from our perspective. No transit, no dip in light. And since we have absolutely no prior knowledge of how any random star's planetary system might be tilted,
The odds of picking a star and having it lined up perfectly are minuscule.
vanishingly small, yeah. It was deemed far too remote a possibility to base a whole search strategy around. You'd have to stare at thousands, maybe millions of stars for years just to catch one lucky transit.
This just perfectly sums up the historical difficulty, doesn't it?
Yeah.
Even when the signal was strong enough transit, the geometry was impossible. When the geometry didn't matter so much, radial velocity, astrometry, the signal was far too weak for the instruments.
Exactly. It took decades of painstaking work on instrumentation, improving spectrographs, developing new detectors, and ultimately, yes, getting telescopes above the atmosphere to finally overcome these immense barriers.
So this early failure of all the ground-based techniques for finding planets specifically, it must have led astronomers to a pretty stark realization.
It really did. The conclusion was that directly detecting a planet, actually seeing it or its effects clearly around a distant star, was likely an impossibility from Earth, at least with the technology at the time.
And the main culprit, as we mentioned with the wobble, was Earth's atmosphere.
Primarily, yes. It's like trying to see fine details at the bottom of a swimming pool while the water's rippling. The atmosphere constantly bends and scatters the starlight.
Turn a sharp point into a blurry mess.
Precisely. It spreads that ideal point source of light from a star into this larger, messy disk that can be anywhere from 0.5 to 2 arcseconds wide, depending on the atmospheric conditions, what astronomers call seeing.
And that atmospheric blurring makes the angular separation problem completely fatal for direct imaging.
Absolutely. Let's go back to our benchmark. The Jupiter twin orbiting a sun-like star at 10 parsecs. If that planet orbits at 1 AU from its star, like Earth does from the sun,
What's the separation we'd see from Earth?
the angular separation on the sky would be only 0.1 arcsecond.
Okay, 0.1 arcseconds apart, but the star's image is smeared out to 0.5 arcseconds or more by the atmosphere.
Right. So the faint image of the planet, separated by only 0.1 arcseconds, is completely swamped. It's just lost, drowned, inside the luminous halo of scattered and blurred light from the much brighter star. You can't pick it out.
Which naturally leads to the idea of getting above the atmosphere, the Space Telescope solution.
Exactly. This was the dream for decades. Placing a large telescope, the sources suggest 2 meters or more in diameter on a space station or as a free-flying satellite completely eliminates that atmospheric interference.
No more blurring, no more scattering.
Well, you still have the fundamental physical limit of light itself, which is diffraction. Light waves bending around the edge of the telescope's mirror. But without the atmosphere, you gain tremendous clarity.
How much better could it get?
The sources note that even a 1-meter telescope objective in space could achieve a theoretical resolution limit below 0.1 arcsecond. And with more advanced techniques like interferometry combining light from multiple telescopes, you could potentially push that measurement down to 0.01 arcsecond.
Okay, so that's the kind of precision you'd need to actually separate the light of a Jupiter twin at 10 parsecs from its star.
Spatially, yes. But once you solve the resolution challenge, the next, arguably even more formidable challenge remains: the sheer brightness contrast.
Right. The star is incredibly bright and the planet is incredibly faint because it's only reflecting starlight.
Exactly. We estimated that a Jupiter twin at 10 parsecs would have an apparent magnitude of about 24. That is exceedingly faint. Trying to spot that magnitude 24 speck right next to a bright primary star, maybe magnitude 5 or 6, it requires suppressing the starlight by an absolutely astonishing degree.
What's the contrast ratio? How much brighter is the star?
In the visible optical range of light, the contrast ratio between a star like the Sun and a planet like Jupiter is roughly 1,000,000,000 to 1.
1,000,000,000 times brighter.
Yeah. You're literally looking for a firefly right next to a searchlight. It's an immense technical challenge for direct imaging.
This must be why astronomers started thinking about looking at different kinds of light. The source emphasizes shifting the search to the infrared advantage.
Precisely. The energy emission ratio between the star and the planet changes dramatically when you move to longer wavelengths into the infrared.
Why does the infrared help so much? Is it because planets are warm?
That's exactly it. Planets, especially gas giants like Jupiter, aren't just cold reflectors. They retain heat from their formation, and they have internal heat sources. They emit their own thermal radiation.
Not just reflected starlight.
Right. And this thermal emission peaks in the infrared part of the spectrum. So if you look at wavelengths around, say, 30 micrometers, 30 meters, that's deep into the infrared.
The planet starts to glow more brightly relative to the star.
Well, the star still dominates, obviously, but the contrast ratio shrinks dramatically. Instead of being 1,000,000,000 to 1, it might only be 10,000 to 1.
Wow, that's a huge difference. 4 or 5 orders of magnitude better.
It's a massive improvement. It makes the detection problem much more manageable, although still very difficult. This insight was crucial, and it drove early proposals for building huge infrared instruments designed specifically to operate in space, like the proposed 15-meter reflector mentioned in the source. They were conceived specifically to exploit this thermal advantage for detecting giant planets around nearby stars.
Okay, so space telescopes, especially infrared ones, were seen as the future. But this brings us to a really compelling, almost tragic historical story that kind of embodies all these early ground-based difficulties. The Van de Kamp case involving Barnard's star.
Ah, yes, Van de Kamp and Barnard's star. This was really the pinnacle of those early attempts trying to use the astrometric wobble method from the ground with extreme dedication.
And Barnard's star itself seems like a perfect target for this, right? It's super close.
It's almost the perfect target, yeah. It's only 1.8 parsecs away, that's less than 6 light years. It's the second closest stellar system to us after the Alpha Centauri system.
But it's not a bright star.
No, it's a very dim red dwarf, only about 15% the mass of our sun. Very faint.
But it moves fast across the sky.
That's its claim to fame. It has the largest known proper motion of any star, 10.3 arcseconds per year. It's physically zooming across our line of sight relative to background stars, which earned it the nickname the Flying Star.
So because it's so close and moving so fast, any wobble caused by a planet should be maximized, right? Easier to see.
That was the logic, yes. And the astronomer Peter Van de Kamp dedicated a huge chunk of his career, 25 years, to meticulously observing this one star from the Sproul Observatory.
25 years. How much data did he collect?
He gathered about 2,000 photographic plates of Barnard's star over that period. This wasn't like modern digital data collection. This was painstaking work, taking photos, measuring star positions on glass plates with micrometers. It was a lifelong, patient quest for that tiny planetary gravitational signature.
And he claimed he found it.
He did. His analysis, published over many years, claimed to show a slight but persistent wavy character to the star's proper motion path, a periodic oscillation layered on top of the straight-line motion.
With a specific period.
He calculated a period of about 24 years for this wobble.
And what did that wobble imply? A planet.
The analysis of that 24-year wobble implied the existence of an invisible satellite, yes. He calculated its mass at roughly 0.0015 solar mass.
Okay, how big is that compared to Jupiter?
That translates to about 1.5 times the mass of Jupiter, and he calculated it orbiting the star at a distance of about 4.4 AU, similar to Jupiter's distance from the Sun.
So, if true, this would have been the first discovery of a genuine exoplanet.
Absolutely. It would have been revolutionary. The first definitive proof of a planet outside our solar system, found through decades of meticulous ground-based work.
And it would have immediately suggested planets are common.
If confirmed, yes, it would have basically solved that mystery, proving that systems far less massive than those earlier invisible satellites were definitely out there. The companion would be a true planet, shining only by reflected light. He estimated it would be incredibly faint, maybe magnitude 30, completely overwhelmed by the star's own magnitude 9.5 light.
But the story doesn't end there, does it? The sources say the result was disputed.
Deeply disputed, yes, and sadly it remains unconfirmed to this day. It's generally not accepted as a real detection.
Why? What went wrong after all that work?
The scientific consensus eventually shifted towards the explanation that the wobble signal Van de Kamp measured was likely not gravitational in origin, but instrumental.
An error in the telescope or measurements?
Probably, yeah. Trying to measure positions with that level of claimed accuracy, micro-arc-second precision, over 2.5 decades, using the same telescope and likely the same measuring engine, it's incredibly susceptible to tiny, systematic, periodic errors.
Like what kind of errors?
Changes in the telescope optics due to cleaning or adjustments, tiny shifts in the lens mounting, temperature effects, humidity changes, maybe even subtle periodic patterns in the photographic emulsions themselves over the years. Any of these could potentially introduce a spurious cyclical error into the measurements that just happen to mimic the signature of a planet with a 24-year period.
And other astronomers couldn't confirm it.
That was the key. Other researchers, using different telescopes and techniques, simply couldn't replicate the discovery. They didn't see the same wobble in Barnard's star. It was a heartbreaking outcome for Van de Kamp, but it serves as a powerful cautionary tale about the extreme difficulty of measuring these tiny effects and the importance of independent confirmation.
It's interesting, too, that the source mentions the alleged planet's orbit was calculated to be sharply elliptical.
Yes, that detail also raised some eyebrows. While elliptical orbits are certainly possible, the large planets in our own solar system have much more circular orbits. Finding a Jupiter-mass planet in such a highly elliptical orbit seemed a bit unusual, perhaps less dynamically stable over long timescales, though it wasn't proof of error in itself.
Okay, so if direct detection methods like imaging were impossible from the ground, and high-precision astrometry like Van de Kamp's was ultimately unreliable for planets back then, astronomers needed another angle.
They had to pivot, yeah. And the angle they took was statistics, trying to infer the presence of planets indirectly by looking at the bigger picture of stellar companionship.
And the driving idea behind this was that maybe star systems and planetary systems aren't fundamentally different things.
Exactly. The underlying hypothesis, which is really powerful, is that stellar multiplicity, having multiple stars, and the existence of planetary systems are essentially two sides of the same coin, different outcomes of the same formation process.
Is there any evidence for that connection?
Well, there's a suggestive piece of simple geometry. If you look at the known binary systems where the stars are relatively far apart, the average distance between the components is somewhere around 20 astronomical units.
20 AU.
20 AU. Okay, how does that compare to our solar system?
It's remarkably similar in scale. Jupiter orbits at 5 AU, Saturn's out at 9.5 AU, Neptune's way out at 30 AU. So that 20 AU average separation for binary stars falls right in the middle of our planetary system's dimensions.
Huh. So it suggests maybe the process that forms wide binary stars isn't all that different from the one that forms planets around a single star.
That's the thinking, yes. It hints that maybe companionship of some kind is just a natural outcome of star formation from a collapsing gas cloud.
So the most compelling statistical evidence for this comes from a specific study mentioned in our sources, the Abbott and Levy survey.
Yes, the Abbott and Levy survey is considered a landmark study. It focused specifically on solar-type stars, stars that are roughly similar in mass, age, and temperature to our own sun, G-type stars mostly.
Why focus on those? Well, partly because we understand them best, and partly because, if you're looking for systems like ours, you start by looking at stars like ours.
And this was a big survey.
It was a massive undertaking for its time. They looked at 123 nearby solar-type stars, all within about 85 light years, and they examined them meticulously using a high-dispersion spectrograph, the tool needed to detect spectroscopic binaries.
Okay, so they were looking for Doppler shifts to find hidden stellar companions. What did they find initially?
Their initial direct observational count was already impressively high. Out of the 123 stars, they found 57 were double systems, 11 were triple systems, and 3 were actually quadruple systems.
Wow, add that up. That's 71 systems out of 123.
Exactly. Which means that even just based on direct observation, 60% of these carefully selected sun-like stars were found to be part of multiple star systems, already showing single stars were not the majority.
But Abbott and Levy suspected the real number was even higher.
Oh, definitely. They knew that the 60% count suffered from a significant weakness, observational selection bias.
Meaning they were missing some types of systems.
Yes. Their instruments and methods were most sensitive to finding companions that were relatively massive, either close in mass to the primary star or massive enough, like those invisible satellites, to create a large, easily measurable spectroscopic Doppler shift.
So systems with really low mass companions, or companions in really wide, long-period orbits, they might have missed those.
They very likely missed many of those. The true multiplicity rate, they reasoned, had to be higher than the 60% they directly observed.
So how did they get from 60% to a higher number? This involves statistics.
This required a bold and, at the time, quite radical statistical leap: extrapolation.
Okay, what did they extrapolate?
They carefully analyzed the distribution of the pairs they did find. They looked at it based on two key parameters. First, the mass ratio. M2, M1s, how massive the companion star was compared to the primary star. And second, the orbital period, how long the orbit took.
And plotting this data showed patterns.
Yes, they created graphs plotting the number of systems they found against these parameters. And interestingly, they immediately identified two distinct types or populations of stellar systems, which might even suggest different formation mechanisms.
What were the two types?
Okay, first, they looked at systems with short orbital period systems where the stars orbit each other in less than about 100 years. In these tighter systems, they found that the number of pairs discovered slowly decreased as the mass ratio dropped, meaning as the companion got much smaller than the primary.
So very unequal mass pairs were slightly less common in tight orbits.
It seemed that way, yeah. It suggested forming a very tight pair with a huge mass difference might be slightly harder.
Okay, what was the second type?
The second type was systems with long orbital periods taking more than 100 years to complete an orbit. Here, they saw the opposite trend. The number of pairs actually increased slightly as the mass ratio dropped.
Meaning wide orbits are more common even when the companion is much smaller.
Exactly. It showed that these wider orbits seemed more tolerant, or maybe even more likely to form, with extreme mass differences between the two components.
Okay, so they have these two distribution curves based on what they could see. How do they use that to find the unseen ones?
This was the revolutionary part. They took these established distribution curves, the trends they observed for stellar companions, and they extrapolated them. They extended the curves mathematically down into the realm of the unseen, moving towards mass ratios far below what they could directly detect, towards the mass ratios you'd expect for brown dwarfs and even large planets.
Whoa! Okay, so they're assuming the trend continues even where they can't see.
That was the core assumption, yes. First, they extrapolated the curves down to a mass ratio of 200 N/1 equals $1,100. That's about 0.01 solar masses, right in the range for the lowest mass stellar companions or maybe massive brown dwarfs.
And what did that predict?
By including the statistical likelihood of those unseen companions based on the curve's shape, they predicted there should be about 20 additional pairs lurking undetected among the 123 stars they surveyed.
Okay, 20 more systems, pushing the total multiplicity rate up significantly.
But they didn't stop there. This was the really bold move. They pushed the extrapolation even further, taking it conceptually all the way down to a mass ratio of 2m1 equals dollars.
Zero. What does a zero mass ratio represent?
Theoretically, it represents the mass contribution of a true planet, an object so small compared to its star that its contribution to the system's total mass is effectively negligible. They were using the statistics of stellar companions to predict the frequency of planetary companions.
And what did that extrapolation predict?
Based on extending the curves that far, they predicted about 25 more systems in this ultra-low mass, effectively planetary category.
Okay, so you take the original 71 systems they saw, add the 20 predicted brown dwarfs, add the 25 predicted planetary systems. What is that total?
71 plus 20 plus 25, that's 116 systems.
Out of 123 stars surveyed originally.
Exactly. It's incredibly close. Within the statistical uncertainties, the total number of inferred systems, including stars, brown dwarfs, and planets, almost perfectly equaled the total number of stars they started with.
That's profound. What was their conclusion from that?
It led them to their radical, incredibly powerful conclusion. Practically all solar-type stars are members of some kind of multiple system. Either they have stellar companions or they are surrounded by a family of planets.
So being truly single, truly isolated, that's the statistical anomaly.
According to their analysis, yes. Companionship, in one form or another, appeared to be the norm, almost universal for sun-like stars.
And did they estimate how many of those would be planetary systems specifically?
They did. If they made a conservative assumption, setting the statistical maximum mass for an object to be called a planet at around the mass of Jupiter, excluding the heavier brown dwarfs from the planet count, their data suggested that approximately 10% of solar-type stars should be expected to have planetary systems.
10%. Even based on this early statistical work, that's a huge number across the galaxy.
Yeah. It was a groundbreaking result. The Abbott and Levy survey, despite using relatively early statistical methods and having uncertainties, remains one of the most powerful pieces of evidence pointing towards the fundamental commonality of planetary systems around stars like our sun. It really shifted the perspective, and the search for exoplanets went from being maybe an observational long shot to looking like a statistical and near certainty.
Okay, so we've established that multiplicity seems to be the rule, not the exception. And we've seen how incredibly hard it was to detect the lower mass end of that spectrum, the planets. Now, we need to talk about the consequences of all this companionship. How does being part of a multiple system actually change the life story of a star?
It changes it dramatically, especially in the closer systems. But first, we should probably touch on how these systems form because that sets the stage for everything else.
Right. Do they form together?
Yeah.
Or does one capture another?
Well, some earlier ideas floated around, like maybe a star spinning really fast could split in two, or maybe stars could accidentally capture each other through complex three-body gravitational interactions.
But those aren't the leading theories now.
No. The collective evidence now strongly rejects those ideas for most systems. The overwhelming consensus supports the idea that multiple systems, binaries, triples, etc., form jointly from the same primordial cloud of gas and dust, much like how we think planetary systems form around a single star.
They condense out of the same collapsing cloud.
Essentially, yes. And the absolutely critical implication of this joint formation is that all the components within that system must have the same age. They were born at the same time.
Okay, same age. Why is that so important?
Because stellar evolution, how fast a star lives and dies, is dictated primarily by its mass. More massive stars burn through their fuel much faster than less massive stars.
So if you have two stars born at the same time but with different masses.
The more massive one will evolve much faster, and that sets the stage for some real drama, particularly in very tight binary systems.
How tight are we talking?
Systems with very short orbital periods, say less than a week, which means their physical separation is tiny, maybe less than 0.1 AU. In these systems, stellar evolution gets fundamentally altered by their gravitational interaction.
Okay, so what happens? The massive one evolves first.
Right. The primary, more massive star burns through its core hydrogen fuel first. When it runs out, it starts to evolve off the main sequence and begins to swell up into a red giant.
It expands, gets bigger.
Massively bigger. And as it expands, its outer layers can eventually reach a critical gravitational boundary called the Roche lobe.
The Roche lobe, what's that?
You can think of it as the gravitational zone of influence around each star in a binary. It's shaped sort of like a figure eight, and the point where the two lobes touch is a point of neutral gravity between the stars.
So if the expanding giant star fills its lobe.
Once the primary star swells up enough to fill its Roche lobe, its outermost material is no longer strongly bound to its own core. It feels the gravitational pull of the companion star almost as strongly.
And the material can cross over.
Exactly. The stage is set for mass transfer. The outer envelope of the giant star starts flowing across that connection point and streams onto the less massive companion star.
Wow. How fast does this happen?
Astronomically speaking, it's quite rapid. It can happen over just tens of thousands, maybe hundreds of thousands of years, which is short compared to the star's billion-year lifespan.
What's the result?
The result is a complete restructuring of the system. The original, initially more massive primary star loses a significant amount of its mass. Meanwhile, the companion star gains all that mass and, critically, becomes the more massive star in the system.
The roles reverse.
Completely. The original primary, now stripped of its outer layers and greatly reduced in mass, might settle down as a subgiant or even a white dwarf eventually. But it often retains a higher luminosity than you'd expect for its new, lower mass because its core is still highly evolved. The entire system structure flips. Mass transfer is a huge consequence of binarity.
Okay, that's one major impact. What else? You mentioned runaway stars.
Yes, the origin of runaway stars is another fascinating consequence linked to the slingshot effect.
Runaway stars. These are stars moving really fast.
Extremely fast. Typically, young, massive, hot stars, O and B type stars, are found in clusters or associations and move relatively slowly through space, maybe less than 10 kilometers per second relative to their neighbors. But we observe these exceptions. Runaway stars that are zipping through the galaxy at very high speeds, sometimes up to 100 kilometers per second or even more.
That's way faster than their peers.
Much faster. And here's the paradox. These massive hot stars are almost always found in multiple systems when they're young. They strongly prefer companionship. Yet these incredibly fast-moving runaway stars are always observed to be single. No companions.
Huh. So where did their companions go and where did they get the speed?
The ingenious hypothesis proposed by the Dutch astronomer Adrian Blau solves both problems at once. He suggested that runaway stars were once members of a tight binary system, and the more massive companion in that pair reached the end of its life suddenly and violently, exploding as a Type II supernova.
A star explodes in the binary. What happens to the other one?
This is the slingshot mechanism. A A supernova explosion is incredibly rapid. The star effectively blows itself apart, losing most of its mass in an instant, which expands outwards at thousands of kilometers per second.
So the gravity holding the binary together just vanishes.
Pretty much, yeah. If the supernova happens quickly enough, basically. If the companion star's mass effectively disappears from the system before the remaining star has time to complete a significant portion of its orbit, then that gravitational link is instantly broken.
And the remaining star just flies off.
It's no longer gravitationally bound to anything. It simply continues moving in a straight line, tangential to the orbit it was following just before the explosion happened. And crucially, it retains the high orbital speed it possessed at that moment.
Ah, so its high speed was its orbital speed in the tight binary.
Exactly. That's where the enormous velocity comes from. It gets flung out like a stone from a slingshot when the cord breaks.
Is there evidence for this?
Yes, the hypothesis is strongly supported by observational evidence. Our sources mention an illustration showing 3 known runaway stars. If you trace their paths backward through space, considering their speed and direction,
They point back to the same place.
they all appear to originate from the Orion Stellar Association, a region of active star formation, and their travel time suggests they were all ejected relatively recently in cosmic terms, maybe 2 to 5 million years ago. It strongly implies there was a massive star death event, a supernova in a binary in that association around that time.
Incredible. Okay, mass transfer, runaway stars.
Yeah.
What's the final, most extreme consequence of multiplicity mentioned?
That would be the formation and powering of X-ray binaries, which often involve neutron stars and even black holes.
X-ray binaries. Systems emitting lots of X-rays.
Extremely powerful X-ray sources, yeah. When the first dedicated X-ray astronomy satellites, like Uhuru back in the early 70s, started mapping the sky, these bright X-ray sources were a big surprise.
Why were they unexpected?
Well, astronomers knew that the remnants of massive stars, neutron stars, should exist. But neutron stars cool down very, very quickly after they form. They shouldn't be persistent, bright sources of high-energy X-ray radiation just sitting there on their own.
So the X-rays weren't coming from the neutron star itself cooling.
Not directly, no. But detailed observations soon confirmed that these powerful X-ray sources were, in fact, compact objects, neutron stars, or black holes located within tight binary systems.
How did they confirm the binary nature?
They saw several key signatures. The X-ray sources often showed long orbital periods on the order of days, which could be seen in optical light variations of the companion star. But crucially, many also showed short, incredibly regular periodic pulses in their X-ray emission, with periods of seconds or even milliseconds.
Like cosmic clocks.
Exactly. These were X-ray pulsars, characteristic of rapidly rotating magnetized neutron stars. And the clincher was observing the Doppler effect on the pulse period itself.
The pulse timing changed over the orbit.
Yes. The observed time between pulses would get slightly shorter as the neutron star moved towards us in its orbit, and slightly longer as it moved away. This periodic change in the pulse arrival times was definitive proof that the compact X-ray source was indeed revolving around a massive, visible companion star.
Okay, so it's a binary. But where are the X-rays coming from if the neutron star is cold?
They're not coming from the neutron star's internal heat. They're coming from an engine powered by the companion star. That engine is accretion.
Accretion. Material falling onto the neutron star.
Precisely. In these incredibly tight systems, the normal optical companion star continuously loses gas. This might be through a strong stellar wind, or it might be Roche-Loeb overflow again, like in the earlier mass transfer case.
And this gas falls onto the compact object.
Yes, that gas doesn't fall straight down. Because of angular momentum, it forms a rapidly rotating accretion disk around the neutron star, or black hole, as in the famous Cygnus X1 system.
Like water swirling down a drain.
A very good analogy, but much, much hotter and faster. As the gas spirals inwards through this disk, getting closer and closer to the incredibly deep gravitational potential well of the neutron star or black hole,
It heats up.
it gets heated to absolutely tremendous temperatures by friction, turbulence, and shock waves within the disk. We're talking tens of millions of Kelvin. Hot enough to emit profusely in high-energy X-rays.
So the energy source isn't nuclear fusion, it's gravity.
It's the conversion of gravitational potential energy into heat and then radiation, yes.
Okay.
And this accretion process is incredibly efficient. It can generate immense luminosity, primarily in X-rays, making these systems some of the most dramatic and energetic phenomena in the entire universe.
And it only happens because of multiplicity.
It only happens because you have that companion star feeding material onto the compact object.
Hmm.
So just like the mass transfer altering stellar evolution and supernovae creating runaway stars, these X-ray binaries are another profound example of how being in a multiple system fundamentally alters stellar processes, creating exotic objects and unleashing violent phenomena that would simply be impossible for an isolated star. Hashtag OutTech Outro.
Wow. This has been a truly comprehensive deep dive.
Yeah.
We started off looking at, the technical details of how astronomers spot a star wobbling.
Uh-huh.
And we've ended up realizing that this whole concept of stellar companionship is actually the fundamental engine driving some of the most extreme stellar evolution we know about. It creates black hole binaries, it speeds up how stars live and die, it launches stars across the galaxy.
It really underpins so much of astrophysics. And the overall takeaway, I think, especially reinforced by those historical challenges faced by astronomers like Struve trying to measure tiny effects, and then the powerful statistical arguments from people like Abbott and Levy, is really compelling. If you meticulously try to account for companions across the entire mass spectrum, from huge visible stars all the way down through brown dwarfs to the smallest possible planets, the evidence strongly suggests that virtually every single star is actually a member of some kind of multiple system. True isolation might just be the real anomaly.
So this research really paints a picture of the universe structured not around isolation, but around gravitational companionship.
Absolutely. And it highlights how the physical differences between, say, an extremely dim, barely self-luminous red dwarf companion and a massive gas giant planet like Jupiter,
Yeah.
those differences are actually minimal. It really just comes down to core temperature, which is driven by mass.
So the fundamental question maybe isn't if a star system forms companions.
But perhaps just what the mass ratio of those components will turn out to be. Will it be two roughly equal stars? A star and a brown dwarf? Or a star in a family of planets?
The implication there is just enormous, suggesting that maybe planetary systems aren't just a lucky accident for stars like our sun, but maybe an inherent part of the star formation process itself.
That's certainly what the statistics strongly point towards.
Okay, so let's leave you, the listener, with this final provocative thought to chew on. If that line between a giant planet like Jupiter and a very faint, self-luminous stellar companion, a brown dwarf, is really so incredibly fine.
Just a matter of a bit more mass heating the core.
Right. And if the statistics indicate near universal companionship for stars, does the universe truly have any single stars? Or are they perhaps all just the brightest, most obvious component of a much larger, often mostly invisible gravitational family?
A family that could include other stars, brown dwarfs, or planets.
Exactly. And if nearly every star is actually structured around some kind of family of companions, what does that ultimately mean for the prevalence and the distribution of life out there in the cosmos?